Good morning, everyone. Can you see my screen? Okay, fine. So let's start today's class. Before I start, let me just revisit the topics that we covered last time. In our last class, we have seen an algorithm to sort few elements, and the algorithm was something different than what we had seen before, like different from uh, insertion sort, selection sort, and bubble sort. In this is the merge sort algorithm, and in this merge sort algorithm, what we do, we divide this array first into two equal halves, and then we sort each of these subarrays recursively. That means using merge sort again on the smaller subarrays, and then we combine them together to get a new sorted array. Okay? And this is the way we write it. And we okay, so we have seen the process of merging to sorted array in details. Okay, just a second. Is it okay now? You're saying voice. Am I audible clearly? Okay. Okay. And then we analyze the running time of this merge sort algorithm, and we've seen like it's a completely different way of argument. Uh, we define some function Tn, which says like when the input size is n, then what's the running time of this merge sort algorithm. And for Tn, we first, based on this algorithm, we first develop a recurrence relation, which is this one. And then we solve this recurrence relation to get a closed form formula for uh, Tn, and which turns out to be n log n. So, any questions regarding that merge sort algorithm? Okay, fine. So, then there's no question. So, it says like you have understood it properly. Okay. So, now today we're going to see another sorting algorithm, and this one is somewhat similar to what we did last time, somewhat similar to merge sort algorithm, uh, but with some differences. Right? And those differences makes this algorithm very fast, and we call it quick sort. Okay. Uh, so let's understand first how does this quick sort work. Right? Let me take again an array. And what is 15, let's say. Okay. So this time what we're going to do is I'm going to divide this array. Something similar to what we did in quicksort. In quicksort also we divided this array. But this time what we'll do, the process of division will be different. The first thing is divide this array. Now, how am I going to divide this array? Is it like still my voice is low? Oh, you're saying no voice. Uh, no, then you check your setting then. Okay, so let's see now how you're going to divide this array. So for division, we'll first uh, pick one element. So let's say I'll pick I'll pick the first element of this array. Okay? And then what I do, so in this case the first element, so I'll call it pivot element. So in this case, this pivot element is 6, right? So now what we're going to do is I'll break this array into two parts such that this pivot element will appear somewhere here, somewhere in this array it will appear, and all the elements that are smaller than the pivot element, that will come to the left of this, and all the elements, let's say this one, suppose I have 6 in here, right? All the elements that are smaller than 6, that will appear in the to the left of 6, and all the elements that are greater than 6, that will appear to the right of this. Okay, someone is saying middle, but it could may not be the middle element. Okay, so I have to compare all the other elements with this pivot element and then decide which part it should go. Okay? So if you think carefully, like I can put 3 to the left of it, I can put 1 also, I can put 2 also, I can put 5 as well, right? So all these elements that are less than the 6, okay. And what are the elements that are greater than 6? It's 9. What else? 12 and 5. Sorry, 12 and 15. Okay. So this one, so although it's coming the fifth place, but that may not be the case always. Okay. And so in this way, I'm going to divide this array into basically uh, two major parts, and one part is trivial. So one part will be having only one element here, that's the pivot element, and the left subarray will contain all the elements that are smaller than p, and the right part will contain all the elements that are greater than p. Okay, fine. Okay, any question? So how? So after this division, this is how the array should look like. We'll have this. Okay. So now what I do? So I'll call it less than, or I'll simply to be with the same notion, I'll say, so so I'll call this one left subarray and I'll call this one right subarray. Okay. Now the second step and the third step will be exactly as it is. I'll call this step 1, step 2 and 3, sort left and right subarray recursively. Okay. So what do you mean by recursively? As usual, I'm going to apply quick sort again on this left subarray and as well as in the right subarray. Okay. And then what would be the third step? Sorry, fourth step. Okay, so after let me draw also. How does the array look like after this step? After this step 2 and 3. So all these elements here less than p, here greater than p, and this one is p, and these are sorted. So once we finish applying quicksort on this left subarray, the left subarray will be sorted, and same as the right subarray, that will also be sorted. Right? Now what? What do you want? So like to get a complete sorted subarray, step 4, I have to combine these solutions. Right? How you are going to combine it? Suppose you are working with the same array. So initially, whatever array that you had, you are working everything. You are doing everything that I am saying on the same array itself. Then how do you, once you are at this position, that means the left subarray and the right subarray both are sorted, and you have p at the in between, right? Then what would be the sorted array of the whole input of this whole thing? Yes, anyone? Yes, I'll come to these questions, how to choose the pivot and all. I'll come to it. So in this case, what we have assumed here, I'll say whatever the array would be, I'm always going to take the first element as my pivot. Now, just focus on this step 3. What we have to do to get the sorted array? Yes, for the left side array, as I said, I have to do it recursively. What does this recursion means? Like, okay, let me do this one quickly for the right subarray. What is the right subarray at this point? Uh, this is 9, 12, and 15. Right? Now, I'm going to sort this right subarray recursively. So again, I'll take my pivot to be the first element of this subarray, and I divide this based on this first element. Right? So how does the array should look like? 12 and 15. This, because there is no element which is smaller than 9. This is how it should look like. Okay. And then how do you get the sorted array of this? Again, so you have to apply quick sort on this left sub array. Sorry, the right sub array, even sub to sub array. Right? So for this, you will take the pivot to be 12, and this is how your array should look like. Right? And once you have this single elements, they are sorted. Right? In fact, you'll have this one as the sorted array, and when you again go up, you will get this one to be the sorted array. And all by all of this, I'm not saying the intermediate steps in details. Rather than that, I'm saying just one word. I am going to sort the right subarray recursively. By that, I mean all of this. Okay, so hope it's clear. We need indexing up to 1. Not clear to me. What do you mean by indexing up to 1? Okay, but okay, I think it's clear. No? What's this? Where to stop up to get one element? Yes, like once I get a single element, it's already sorted. I can assume. Right? So it's just one element. It's sorted trivially, right? And that's the stopping criteria. And then once I have a single element, then I can move up. Right? That's the conquering approach, like merging the solutions, combining the solutions. Right. So by doing that, eventually I'll get the same array as the sorted array. Right? And for the right sub array, what I'll be getting after like applying the whole process of quick sort in the left sub array, then I'll be getting like this is what I'll be getting. This is the one. This is the, right, and I'll be having in the middle 6. Now, what do I have to do to get the sorted array of the whole thing of this whole array? We are at this setting after step 2 and 3. Point is, we don't have to do anything further. Right? So here what we have 1, 2, 3, and 5. I have 6 here, and then I have 9, 12, and 15. Right? This is the part that we have obtained by applying quick sort on the left subarray. This is the sorted array sorted part that I have obtained by applying quick sort in the right subarray. And see what's the status of this array now. All the elements that are to the left are all smaller than the pivot element. To That's from the step 1, right? And after step 3, this part is also sorted. Right? So this one is sorted, this one is sorted, and 6 comes in between. Right? So this combining step is actually trivial. We don't have to do anything there. It's like once I finish the step 3, then this array will be a sorted array. It's okay. Now at this point, I want you to think a little bit and compare this process of quicksort with merge sort. What are the differences can you find out? The pivot one first. Yes, there is no notion of pivot, right? In merge sort. That is one difference. And by the way, this difference is basically in the, so basically you are saying that we are using a different approach in dividing this array, right? In merge sort, we divide it into two. We figured out what's the middle index, and then we divided it. So it was giving me roughly equal parts, right? Now we have again division step in this quick sort as well, but this division is completely different than the previous one. And for this division, I need to pick a pivot element first, and then based on this, I have to make a partition of something like this. What does this tell you? This tells you something interesting. Here, can you tell me what are the sizes of this left subarray and the right subarray? What is the size of the left subarray? So when I ask you this question, like it's not, uh, don't only focus on this particular example, but try to think in general. So it's a mid minus one. I'm not getting what is mid. Oh, so like it's you're saying n by 2 minus a 1. No? P minus 1, n minus 1 minus p. Okay, yes, I like uh, p is okay. P here is not an index. P here is not an index. P is the pivot element. That element 6 for this example. Okay, someone is saying again n by 2 minus 1 or n plus 1 merge or the idea is equal, but here it can be anything. It could be greater or less than the other. This answer is correct. The point here to note is that since our division is dependent on the value of this pivot element 6, right? So the size, I cannot tell you what would be the size of the left subarray, what would be the size of the right subarray. That I cannot guarantee beforehand. Why? Because it's completely dependent on the value of this. For example, when I chose this pivot element to be 9, while applying quicksort on this right subarray. I've chosen this as my pivot. What is the left subarray? There's no element smaller than this. There's nothing, right? So size of the left subarray is 0. You got the point, right? So this time I'm not partitioning the array into equal halves, or even I cannot tell what are the sizes of the left subarray and the right subarray. That is an important difference from quicksort. Okay. Yes, it all depends on the pivot element, value of that pivot element. Okay. And we have another significant difference in, like, as I said, step 2 and step 3 are the same. We have to apply recursion, right? Now, step 4, in this quicksort, this step 4 is kind of trivial, right? We don't have to do, once I finish this step 3, this array is already sorted. But just recall, we have to do something non-trivial while merging two sorted subarrays, right? Something that we discussed, all of this. A merge function we defined there, right? So that part was not at all trivial, right? Whereas in quicksort, once you finish doing the uh, recursion for both the left subarray and the right subarray, then we are done. Non-trivial means not unique. Non-trivial means like trivial in this case. I'm saying we don't have to do anything. Right? It's a not obvious. Okay. Yes. And in case of merge sort, it's not obvious that like how to combine. You have to do something, some kind of manipulation you have to do, arranging those elements to get a sorted array. Right. These are the main two differences between these algorithms, right? Division step is completely different. As a result, we are not able to guarantee what's the size of the left subarray and the right subarray in case of quicksort. Whereas in case of merge sort, we can guarantee that it's going to be, subarrays are going to be of equal sizes. And in the conquering step, merging them, combining the solutions, that step is trivial for quicksort, but it's highly non-trivial for not obvious for what to do for merge sort. We have to do some kind of manipulation there. Okay, right. So now what I do, I'm going to focus. Also, now I'll again spend some time on this step 1, how to make this division. Okay, so I just here, from going from this array to this array, I've just directly written what are the elements that are to the left and what are the elements that are to the right of it. Okay. But since I can look, this is a very small array and I can see all these elements, I'm just putting them using my uh, um, some calculation I'm doing in my mind, and then I'm putting it in this particular array, right? But while writing the code, you have to specifically tell what are the steps that you are following from going from this array to this array. Okay. So now I'm going to explain this step 1 again. So what is the status here? So I have this particular element that I have chosen as my pivot, and there are few other elements there. One question, so how do you choose pivot element and what is its basis? Okay, as I said, for the time being, let's assume that we are always going to choose the first element as the pivot for the time being. Okay, and then I'll see how to make change. What would happen if I make any changes? What is the oh, revisit? Okay, sorry for that. uh, okay, so this is the array. So I have pivot sitting over here at the first position, and what I want something like this. So this pivot should be coming somewhere here, and all these elements should be the less than p, all these elements should be the greater than p. Okay, uh, fine. How to do this? How to get such an array? Yes, anyone? Okay, so let me tell you so what to do. So first, let's say let's see the easier option here. uh, I'll take another array. Say I have these elements here. Okay, so what I'll do, if pivot is the smallest one, then what? Yes, what would happen if the pivot element is the smallest? For example, exactly that situation occurred in here. Then no left subarray. Yes, the left subarray will be empty. All of these kind of non-trivial things might happen. So now to divide this array in this way, what I do, I'll take an index running variable k, which indicate these elements, right? And I'll take another separate array. I'll in this array, let's say this is my initial array A. I'll take another array B, and in this array, I'm maintaining two indices. Right? One is I, another one is J. I is sitting at the very beginning of this B, and J is pointing to the last cell of this array B. Okay. So what am I going to do is I'll take this AK and I'm going to compare this AK with the pivot element P. Okay. So I'll make this comparison AK and P. Right. What if I see that the element AK is smaller? then what I should do? So say, let me say, if AK is smaller than this, where should this element I put? I'll be putting those elements from the beginning. I'll keep on putting these type of elements, the elements that are less than P, I'll be putting them from the beginning of this array. And how do I know the beginning? And this index I here will help me in that. So in that case, I'll be putting BI to be this element AK. Everyone getting it? If AK is smaller than P, then I'm putting it at the very beginning. And what else should I do? That says that this element is coming here. Okay. So then after doing this, I'll increment my K. K will now point to this element, and also I will point to the next free location in the B array. So that means I'll increment this K and also I'll increment this I. Okay, is this clear? But what if the element AK is greater than P? Where should I put this element? Suppose let's say this element, the red one, is greater than P. Where should I put it? I should be putting this element at the very end of it. Okay, so what should I write here? Bj will be AK. Yes. And what else do I need to do? I will increment K to check the next element, but this time I'll be decrementing J. Okay. So now this time this will be K. K will point to this location now, and this element comes here, and J will point to this one. Okay, so I have to do these things only, right? So I keep on comparing this pivot element or all the other elements with the pivot element, and if I see that element is smaller, then I'll put it from the beginning of this B array, and if I see that element is greater than the pivot, then I'm keep on putting them from the end of this B array. Is this clear? Okay. So just to make sure everyone understood this, just I'll do this step again. See, I'll take this array. Okay, this is the array. So I'll take another array B. Okay. Now this is my P. This one is my pivot element. So I'll compare this 3 with this pivot. So it should, so this is my A array, this is my B array. So this 3 will come here. Right? So 9 is greater than 6. So this will come here. 12 is again greater than 6. So 12 will come here. 1 is smaller than 6. So 1 will come here. 2 is smaller, 2 will come here. 5 is smaller, 5 will come here. Right? Then 15 is greater, 15 will come here. Right? So after the end of putting all the remaining elements of the A array, I will be left with only the pivot element in the A array, and I will have only one slot there. Right? And then finally, I'll copy the pivot element in here. So P is this element, all the elements to the left are less than P, and everything here greater than P. Okay, fine. So I think this is fairly easy one. It's one thing. It's a byproduct of this process of this partitioning. So I'll call this process partition. So this process actually gives me one very important information. This process gives the correct position of what, can anyone, let's say, fill the gap? After this partitioning step, one element of, yes, of the pivot element. Right. Note that the pivot element is always going to get its correct position after this partitioning step. Correct. Right. So that is one important aspect of this. Okay. So in this partitioning process, what we have done here, we have used in this process, we have used an additional array. Okay. But the question is, can we do it without using any additional array? Do you get my question? So here I have used an additional array B. I'm copying them, everything, all the elements of A in the B array, and then I can copy them back to the A array. Right? But I am actually using this additional array. It's a, I was solving this array and just got into loop. Yes, you have to use a loop. Okay. So what would be the loop? You can use a for loop there. So these are the only conditions I have named here. You can use a for loop for k runs from this value. If you take this value to be L and this value to the R to be the R, so L runs from K L to R. K runs from L to R. Additional array are different from the partition one. Yes, I'm using some kind of additional array here, right? But I don't want that. So, I mean, if there's no other option, I have to do it. Uh, but it would be better if we can do this all these partitioning thing within the same array itself, within the array A itself. Let me just give you the idea of this. We can use sorted array as well. Yes, we can use. There's no harm in using any additional array, this array B. But okay, so let me tell you why I want it to be done inside this array A itself. Right? Uh, in the very beginning, I said that the running time is not the only way to measure the efficiency of an algorithm. Can you recall that? Running time, how fast an algorithm runs, that is not the only way to measure the efficiency of an algorithm. There could be some other ways of measuring efficiencies, and another way of measuring efficiency is the memory, right? Space. How much additional memory does your algorithm using? So if I implement this algorithm in this way, the way I described here, I am actually using another array of size n, right? Space is also important. Very, very correct. Very much agree with you. Right? But if that's why I'm saying there's no harm as long as you are only interested in the running time. But to make it more efficient, it would be better, if possible, uh, try to make this partition within the same array A itself. Okay, are you getting my point? So now let me tell you how to make this partition within the same array itself. Okay, so uh, so first I'll give you the high level idea, and then I'll write the code for you, like pseudo code for you, not the actual code, pseudo code for you. Okay, let's start. So I have this array P here, and all the elements here are not partitioned at all. A is this array. Suppose that I'm able to uh, make make a partition not of the whole array, but some part of it. Like, let's say up to this, I'm able to get this type of arrangement. Okay. Okay. So up to this, I'm able to get this, like this part partitioned, and this part is yet to be partitioned. So suppose somehow you are able to get something like this, then what you are going to do? Now we're going to take this particular element here and compare it with the pivot element. If I see this element is greater, then what should I do? Then I can claim that up to this much we have done this partition. So I can say up to this is something that we have already partitioned. If that particular element, if this particular element here is greater than this. Yes, are you getting this? Now, if this element is smaller, where should it go? I'm going to put this element somewhere here. By the way, this element here was also greater than P. Right? This element here is greater than P, so I'll swap these two elements. This element I'll take it out in here, and this element I'll put it this one. Okay. To get the idea of this, and I keep on doing such thing. Okay, let's write the pseudocode. I think it will be helpful. So to write the pseudocode, I'm assuming the indices in general form. Right? So the first index, I'll take this L, the left index. I'll say the R to be the right index. What would be the pivot element for us? This is the array. This is the portion of the array in which I am applying quicksort. Since it's a recursive process, I have to apply quicksort. I may have to apply quicksort at any part of the array, right? So that's why I am assuming this. So the left index is L and the right index is R. Within this range, I am applying quicksort. The first step is to do the partition. Uh, if this is the portion of the array, this is the subarray, then what would be the pivot element according to our assumption? L, yes. So A of L, A is this array. So my pivot element is AL, right? I will take the index I for this one. I is the index. I'll start with L plus 1. Okay. And I'll do the something similar to what we did earlier. So for all the elements, J will run from L plus 1 to R. Right. All these elements, I'll be comparing it with the pivot element. If I see A, J, like this element, I'll write J here. Right. I is this one, J is the running index for all these elements. Right. So if I say that this AJ is smaller than P, then what should I do? Then I'm going to okay. Let me write it, and then if you're not getting, then we'll discuss it. So I'm going to swap AJ and AI. So although so in this case I and J at the starting position both are the same indices, right? So this will be the same thing. This swapping will not have any effect. But after that, I'll do this one. I will be I plus 1. And this is the only thing that I have to do. And for every element, this is the thing that I'm going to do. Okay. So let me take a general setting. Let's say up to some point we have achieved some kind of partition. Let's say at some point I is somewhere here, and up to this point we have done this partition, right? And suppose J is this index. Okay. So what is the interpretation of this I? This is the first element. This is the index of the first element that is greater than. So this portion is greater than P. All these elements in this portion are greater than P. I is the first index, right? And all these elements here, they are less than P. Okay. And I'm trying to adjust this jth element here. So what is the process is saying? What is this process? If I see AJ is smaller than P, this is my P element. If I see AJ is smaller than P, then what am I saying here? I'm going to swap these two elements, right? So as a result, what would happen? Right? Suppose this. Okay. So when I do this swapping, then what will happen? This particular element like AJ will come here. So if I draw the similar thing, this is my P, this is the index L, right? So earlier up to this point it was sorted. Now when I do this uh, thing, when I do the swapping, so this element is smaller than P, so that will come here. So up to this point, all these elements are smaller than P, right? Up to this point. This element also, that jth element has come here, right? And from this point onwards, what is the element that I have come here? that the ith element, earlier this ith element came here, right? This particular element was greater than the pivot element. So this portion is greater than P. Okay, are you able to follow this? Okay. So then once we are done here, so then I'll try to put this element in the proper place. If this element is less than P, again I'm going to swap it with this element here. The first element that is greater than P, I'm going to swap it with that. Okay. And if the element, then this element is smaller, then that says that, sorry, if this AJ is greater than the pivot, then this says that up to this is also greater. Give an example. Okay. Okay. So it's, I'll do it. I'll add one. Let's take the same array and do this partition. Okay. So 6 is the pivot element, right? Now this 6, so this is my J now. Okay. And this is also I. Okay. Now if this is smaller, right? AJ is smaller than pivot. Okay. So I'm doing the swapping, but after the swapping in this initial stage, this is still your this is like I'm saying swap AI with AJ. Like both of them the same element. This swap doesn't change the configuration of this array. Okay. So now J comes here and not in this array. So let me do it in this one. So J goes here, I also goes here. Okay. Now this 9 is greater than, so by the way, I'm not using any other array, just for the sake I'm writing it. Right? Now this AJ is greater than this pivot element. This is your pivot element. 6 is the pivot element is 6. Right? AJ is greater than this. So then what should I be doing? I'm not going to do these things. I'm not going to increment this I, right? So I'm just going to increment J here. So I will remain the same and this will be my J. Okay. Again, now I'll be comparing this 12 with 6. 12 is greater, AJ is greater. So again, I'll not be doing this stuff. Rather than that, I'll go to the next element. So now my J will be this. So at this point, I want to say that the point that I was making. This is the pivot. This portion of the array having elements less than P and this portion of the array are having elements greater than P. Okay. Now we have, is this clear? The situation that I was describing here. some portion of this array is now partitioned. I have to make the partition of this portion of this array. This portion of this array is somehow partitioned, right? So now when j is 1, sorry, not j is 1, aj is 1, then I'll be comparing aj with the pivot. So this time I get aj is smaller. I should be doing this. So I should be swapping. What are the things that I should be swapping? AI with aj, right? Swap AI with aj, right? If I do this swapping, what would happen? So this will be 1, this will be 9. Okay, fine. And then j will be incremented to this. J will be incremented to this, right? Now see, I okay, I'm also going to increment I as well. So I will be here, right? Now see the situation of this partitioning. I can say up to this point I have made the partition. And what is this? Like this is no longer valid. Up to this, these are the elements that is less than P. These are the elements that are greater than. Got it? Now again I'll do this swapping. First compare AJ with P. AJ is smaller. I'll again swap AI and I'll get 2 here and I'll get 12 here. Okay, after this swapping. So I'll be incrementing I and I'll be incrementing J. This will be my I, this will be my J, right? Okay, so now this time I have made even more progress. So this portion is P and this portion is, sorry, this portion is less than P, this portion is greater than P, right? Again, I have J, AJ is smaller than P. I'll make this swapping, right? So I'll have 5 here and 9 here. I'll be having, sorry, I've written the same thing. I'll be having 5 here and I'll be having 9 here, right? Okay, so my J and I will also, this will be my I, this will be my J now, right? So this part is, I have also done this progress here. This is greater than P, this part is less than P, right? Now what? AJ is greater than the pivot, right? So I just increment this J. So like this has to be done up to the end of this array. That's what we have done, right? So after this point, then these are the elements that are greater. These are the elements that are greater. Are we done yet, or do I have to do something else? By the way, where is your index I? This is the index I. And J goes beyond this array range. Okay. So now, so are we done yet? So have we got the partition that I was looking for? No, not yet. So I have to put the pivot in the correct position. what would be the correct position of the pivot? It should come just before middle of P6, should be before 9. No, so if I put 6 here, then 12 will be some element which will go to the left. It should not happen, right? Before I, yes. It should be just before I. It should come somewhere here. And what can I do? Am I going to shift everything one step back, or I can do something else? Yes, I'll do swap. The AL, like the pivot element, I'll swap it with I minus 1. Correct. So after this for loop, I should be doing a swap. This swap is after this for loop. Okay. I'll be swapping AL with a I minus 1. Right? So if I do that, then I'll be getting 5 comes here and 6 goes here. Right? So then these are the elements that are less than P, and this is my P. Right? And this is exactly what I want. The system. And what should I be getting as an output of this process? This is the process of partitioning. Partitioning this array A, right? And what range of this partition I'm doing uh, on this array A from L to R. Okay. So what should be the output of this process? Just to separate these things out. What should I be returning? As I said, that this partition process gives the correct position of the pivot element. What should I be returning? Correct position of this pivot is here. What is this location? How do you get it? Anyone? Correct position of the pivot? I minus 1. Yes. So I should be returning, it's I minus 1. Okay. By swapping it with I minus 1. Yes. So I have already done. AL I have swapped with AI minus 1. The position of the pivot is I minus 1. Position means like the index where this P is sitting, that's the position of the pivot. Okay. So in this context, so I'll write it. Write this pseudocode of quicksort in this way. So suppose I'm applying quicksort in this range of this array, right? With so within this portion from L to R, I'm applying quicksort. Right? Some base case I will say, so what happens if L is greater or equal to R? Is it possible? The left index is greater equal to the right index? No, like the only thing possible is that L is equal to R. That is possible, right? But what does that mean? L is equal to R, left index of the portion is same as the right index. Is it possible? Yes, that means we have only one element. In that case, we don't have to do anything. We'll just return, right? So other than that, what I do, I'll take the pivot element. Okay. Which one I'm going to choose as my pivot element? The first element I'll choose as pivot element, right? And then what I do, I'm going to partition this array from L to R. Okay, and so this partition will return me the position. Let's say I say J is the position of the array after being partitioned. Let's say so after this partitioning step, I'm having P over here and J is this position. So L and this is R. Right? So what is the left subarray now? Left subarray. In the left subarray, I have to apply quick sort on the left subarray. And also I have to apply quick sort in the right subarray. How can I specify? Yes, in the right also. How can I specify? So suppose this one is for the left subarray. How do you write recursion in this way? So look in here. So what does this mean? Quicksort ALR. That means in the array A from this index L to this index R. Right? So for sorting this left subarray, not P minus 1. So it's not A L P minus 1. This is not correct. Why? Because P is the pivot element. But here I have to mention its position, its index. It should be J minus 1. Correct. So this portion, this position of P is J, and before it I have J minus 1. This portion is the left subarray, and this portion is the right subarray, right? And how do I apply quick sort in the right subarray? It's like A, then J plus 1 to R. Okay. 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 Now I have a few questions for you to think about. The questions that you were asking, which one should I pick as pivoted? Can I pick any one of these? Or like, why are you choosing the first element as pivot? Right? What if I choose any one of the elements as my pivot. So, for example, I'm saying like I'll choose the ith element as pivot. Okay. P is AI. Pivot. My pivot is AI. Right. So this is L. This is R. I have, let's say this is the index I. I choose this element as my pivot. First is convenient. Okay. So, but still, suppose I want to always I want to choose the fifth element as pivot. How do you change your algo? You can do this thing. Let me write it. This changed version. It like this pivot element. I'm choosing it slightly different. So I'm saying you choose the pivot to be the ith element, okay? And then to follow the exactly same setting, I can do a swap, and I'll bring the pivot that you have chosen at the very beginning. Right? That means although you have chosen this element as your pivot, so I'll interchange these two elements. Then I am in the position that this element is the pivot. This element is the pivot. Right? Then it's exactly the same thing that we have written here. Then we do the partition, quicksort, apply quicksort in the left subadic, apply quicksort in the right subadic. Okay. Okay, that's fine. There's nothing special about the first element. I can choose any element as my pivot. Okay, does that answer all of your queries? Okay, fine. Now the point is, what about the running time of this process? Running time of this process. For that, I'll also put few questions. Suppose the pivots are chosen in such a way that we always get 1:1 partition. Then what is the running time? Do you got this question? We'll discuss this question answer to this one later, but it's important to get the question, understand the question first. So what I'm saying, you're choosing the pivot elements in such a way that you will always get equal partition. Right? Not a partition of this kind, not a partition of this kind. So this is a good, nice partition. So if I choose this first 6, then I'm getting, I'll be always getting 1:1, roughly 1:1. Right? I should be saying roughly, as I said before, like in case of merge sort. Roughly means can you can anyone tell me what do you call such an element? What do you call which one? The element which whose correct position is always in the middle. What do you call the element which comes at the very middle position of a sorted array? Yes, right. We call that median. So if I or to put the same question in a slightly different way, and by this one, this is almost 1:1 partition, and this pivot, this chosen pivot, this is the median. Right? I always pick the median element. Right. Then what would be the running time? I'm leaving this question for you to try out. I'll have another question for you. What is the opposite of this? Opposite of this means that uh, pivot is always the minimum or the maximum element. Then was the running time. It's very important to understand these two situations when you have half partition and when you have a very unbalanced partition, like all the elements are going in one part, another part is zero. What would be the runtime of uh, of this quicksort process if you have such if you have these two cases? Okay, you understand this problem? Will 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 you discuss this one, or I'll ask the TA to discuss this for you. Okay. Any questions? In login for best case. I don't know what is the best case. So if you are saying that n login for the best case, then you have to tell me which one of these cases is the best case. Is it the case in question 1 or is it in question 2? 1:1 partition. That is the best case. Yes. And the question 2, minimum, choosing minimum or maximum, that is a bad case for us. Right? And I want you to prove, and in the worst case, what would be the running time? Okay, so you try to figure it out. Okay, it will be n squared, right? So I want you to have a proof of these situations, right? I want you to get the proof of this. Anyway, like these things will be discussed in the tutorial class itself. Okay, fine. So I'll stop now. If there is no question, then I'm stopping here. Any questions? Okay, so let's since there's no question, let me close here. Thank you, everyone.